Hi, I'm Abhishek, and I will be presenting to you about my final year project, which is Multivariate Earthquake Prediction. So let us run through a quick introduction. So this graph represents the number of earthquakes that have a magnitude greater than 7.5 since 1980. So as you can see that this graph gives us a holistic idea of the frequency of such earthquakes, and it doesn't seem a lot. Let us look at the infographics as to the amount or expenditure based on such natural disasters. As you can see, from in 2010, around $200 billion was invested just in earthquake relief and earthquake funds. The extent of damage caused by earthquakes are quite devastating. Now, the purpose and objective of our project. As evident from the statistics, earthquakes pose an immense threat to human living. The extent of damage caused by such earthquakes is by far one of the worst natural disasters. The main aim of this project is to address the problem of forecasting such natural disasters. We employ a wide range of techniques to solve the problem of forecasting earthquakes. Some of the main topics that we will be covering throughout the presentation is 1. The dataset, the current research for forecasting, the proposed solution for our current forecasting problem, and finally discussion and conclusion based on the results that we obtain. Now let us talk a little about the dataset. The dataset obtained from 80 open source datasets. This data is collected from seismic sensors placed across the South China Sea. So the number of sensors is around 100 to 140, and each of these sensors gives us a unique dataset with the readings. The data consists of electromagnetic and geospatial features, which can be considered as covariates for our training data. Now let us look at the current research for forecasting. Now the current research includes statistical models, transformer models, SCINet models, and ensemble models. Further sections will cover a bit more of detail about each of these models and how we have used them in our current research. So statistical models are quite famous in forecasting scenarios. The models that we test out are, for example, ARIMA, SARIMA, VAMAX, and a few other models. The problem with these models is that the data needs to be appropriately transformed using, let's just say, differencing or log transformations. Now, when does this come into play? For example, if the data is going to be exponentially distributed, then we'd have to consider log transforming in order to normalize data. So testing of these models was performed with a maximum of 96 lags for both the AR and MA components. Let us move on to the transformer models. Now the transformer model, in particular the informer model that we will be following, has a transformer backbone. It follows the encoder-decoder architecture as that of a transformer, and as you can see that each of the encoders or decoder layers have a particular self-attention attached to them. Let us look at what I mean by self-attention. Now, as you can see that we have an input sequence across multiple time steps. This is then embedded into an embedding sequence. Now, the attention mechanism concentrates on just specific features. So, for example, if we have 4 different attention blocks, then the embedding sequence is split into 4 equal length vectors. Now, as you can see, the dark blue colors is the feature that each of the attention block concentrates on. In this case, we can model the changes across temporal dependencies based on different time steps. So the purpose of using our informer model is due to its ability to model long-term temporal dependencies. It is useful for a high case due to the high variability of data across time. So the informer model, as we use it, has been completely trained from scratch using the AETA dataset. We use 6 attention heads with a training window of around 96 time steps along with a prediction window size of 48 time steps. Let us move on to the SCINet model, which is a part of the convolutional models. Now the SCINet model uses convolution layers in each of the network block. The model is designed like a tree structure wherein each layer consists of 2n number of blocks. So n represents the number of layers here. Each encoder or decoder layer contains multiple self-attention units to capture information similar to that of an informer model. Now let us look at how the mechanism of the SCINet works. So as you can see, the first level is a SCINet block. The feature vectors are then split into 2 different SCINet blocks, each of the SCINet block being able to model specific spatial features. The final level again has 4 different SCINet blocks, each of them concentrating on their specific features. Now as you can see, the number of features that each of these blocks concentrate on or learn from are quite different and are much more extensive. So the purpose of us using the SCINet model is to capture spatial dependencies. It is useful for our case due to the multivariate data structure for our particular forecasting model. So similar to the informer model, the SCINet model has also been trained from scratch using 3 levels of SCINet blocks and training window of 96 time steps. It has a prediction window size of around 48 time steps. So let us look at a few challenges with forecasting. Current problems with forecasting is the high dimensionality of data. Appropriate feature selection or extraction is required to model the dependencies in data. Furthermore, using neural network models requires the data features to be mutually independent or uncorrelated. So we address the problem using three feature selection techniques: the correlation coefficient, mutual information, and neural network feature selectors. The correlation coefficient and mutual information assign scores for pairs of features, and these scores will have to be less in comparison between the two features while maintaining a higher score with the target variable. The neural network feature selector, on the other hand, uses a network pruning algorithm. Now, we will not be going into further detail with all of these methods due to time constraints. So, what is our proposed solution? Our pipeline consists of three separate components. First, we perform feature selection on each dataset to get the final subset of features, following which these feature vectors are passed through the Informer and SCINet models. These models generate embeddings and predictions from the two models to test training losses, following which the embeddings are used to train ensemble models such as LSTM and random forests. So this is a holistic view of our entire proposed solution. So let us look at the results from statistical models. Now these models, namely ARIMA, SARIMAX and VARMAX, are three best performing models. Therefore, we take these three models and compare the predictions for the magnitude power. So as you can see that the predictions in dotted orange line is nowhere close to the true values. This can be accurately said that the performance of these statistical models isn't as good or as significant to the data. What about the neural network models? So neural network models has quite a bit of train settings that we have experimented with. So first and foremost, we fixate on the number of training epochs. So initially we train the SCINet and Informer losses with the train settings, and as we can see that both the losses diverge at about around 20 epochs. So this kind of tells us that we'd have to limit the number of epochs to 20 in order to maintain comparability. So these are the training results for each of the different models, and as you can see, the number of datasets that have been tested out is also different. A random forest model with mutual information feature selector by far performs the best compared to all of the models. Note that we have also highlighted two other scores, which is for LSTM ensemble for the NFS feature selector. Let us get into more detail about that a bit later. So this gives us another idea as to how the losses are distributed, and as you can see in every scenario, the random forest performs much better while the LSTM model tends to perform worse when compared to random forests. However, let's take a look at the predictions. Now as you can see, the random forest model is quite conservative in trying to predict. Despite the lower losses, you can easily tell that the predictions are not as accurate and will not be acceptable. The LSTM model, however, had a higher loss. It is able to predict much better when compared to the real world data. So as you can see here, most of the spikes have been appropriately modeled by the data. So in conclusion, we can see that despite lower losses, the random forest performs quite poorly in predictions. What is the final conclusion that we can draw from our entire research? So our research includes extensive testing of different types of models. It is evident that the statistical approaches were unable to model the change in data possible due to its high variability. Ensemble models using two different learning mechanisms perform much better in comparison. Despite higher losses, LSTM model performs the best in predictions, inferring that relying solely on losses may not suffice. That concludes my presentation for my final year project. Thank you for watching.